I'm leaving the floor to Simone Mucci and Marco Cecchini. No, I had to say that. So, well, after thanking myself for leaving the floor to myself, what can I say? This paper is quite exciting. It is I think it's our first hybrid paper. So please, everybody here and from home, bear with us because it is experimental, not only in the approach, but also in the practice. Let's see how this goes. It's truly my first time, and we are sort of even combining slides with a handout again. It's a new idea. Now, I think I already introduced Marco Cecchini at the beginning of this event. He is a PhD student at Sapienza University of Rome. He is a mathematician, and yet we are both teachers. And these reflections actually started again in the same bookstore mentioned before. So you see, how precious that place is for us. And yeah, again, so these reflections originated from actual teaching practice, which is what I like best of this idea. Now, Marco will introduce you to the concepts of algorithm and heuristics as we conceal them. I would like just to stress for the audience that for quite some time, I asked Marco, like, how would you define this heuristic approach? How do you define an algorithmic approach? Our theoretical framework is evolving. So my personal feeling is that the theoretical side, so algorithm versus heuristics, and the continuum and the quantitative differences between these two learning approaches are a truly inferior concept. And at the same time, the practical application for the analysis of what goes on in a classroom, well, that really works. And again, my favorite thing of our idea is that thanks to the dialogue between mathematics and classics, something new is emerging or is trying to emerge. Now, without further ado, Marco, if you are ready, I am leaving the floor to you. Please, at your convenience.
Thank you. I'd like to thank the Center for Hellenic Studies for having me here. And yes, I'd also like to underline that all of this is born from necessities, mine and of Simone, the necessity to understand what is not working in our school, in our classroom, the necessity to teach better, and the necessity to study and learn and understand better ourselves as students and researchers. Being said that, I can start with the presentation. Okay. Do you see the presentation?
Yeah, we can see them perfectly. I don't know whether you want to go in the full screen mode or whatever.
Yeah.
Okay, it's already the full. So my apologies, Marco. It works perfectly.
Okay, thank you. In this talk, I'm going to define two ways of thinking, the heuristic way and the algorithmic way. To learn algorithmically means to study every information as separated from all other. To learn heuristically means to focus on the connections between facts. To learn algorithmically, you need to rely more heavily on memorization, often in mathematics, of a mechanical procedure or a formula. As an example, to study history algorithmically is to memorize every date. To study it heuristically is to focus on the causal connection between events. I will argue that much of our reasoning happens in a spectrum between these two extremes, and that much of the difference between these extremes is quantitative. This quantitative difference is the number and complexity of information that are contained in a single idea or word or symbol. As an example, one could take a text and learn it by heart, or use concept maps. Each word of the second case, the concept map, contains the information of many words in the first case. We believe that the most effective way of learning is to start memorizing the most simple examples of the phenomenon subject of study, so an algorithmic part of learning, to build up an intuition of the problem, a heuristic. A heuristic, which is a model made of connected complex parts, each of which synthesizes many information. Then, through the heuristic, create some kind of algorithm or formula which makes possible to analyze more complex examples. Having now access to a vaster dataset, one can create more general and more efficient heuristics and start a new cycle. More general and more efficient algorithms that lead to understanding of more examples, and so on. This method should guide both researchers and teachers. I'm going to argue that our current educational system has a strong bias in favor of the purely algorithmic way of learning and explaining, especially outside of universities. Mathematics is taught as a set of rules and formulas to memorize, a set of instructions for a procedure which, given an input, will mechanically produce an output. Simone will argue something analogous on his field. We do not believe that this is an effective way to transmit or acquire knowledge and teach critical thinking skills. We think that to only teach algorithmically is to teach to execute instruction, which might be complex, but without asking questions or understanding the reasoning behind. Furthermore, with the heuristic comprehension, it is possible to derive many facts, even some not previously known, through the knowledge of few informations. There is also a psychological aspect. Students who are taught algorithmically and therefore initially don't understand the subject are demoralized and don't think themselves able to understand the general aspects, and so rely more heavily on memorization and algorithms. But this understanding is fragile, like a house of cards. Being the links between the cards few and weak, the breaking of just one of them can have catastrophic effects. The anxious student can easily forget just one fact or detail and break down. This leads to more insecurity and anxiety, and so to more memorization in preparation and forgetfulness during tests. This can make a student hate and fear the subject. The student, which is able to learn and execute the algorithms, will get good grades, but will probably find the subject dry. In both cases, the student will be robbed of the understanding and beauty of the subject, of the curiosity it can elicit, and of all of its usefulness. So, now we will proceed with some example, which me and Simone will show you. The first example from me and the first example from Simone will clarify how to use our proposed method. All the successive examples will show how using heuristics diminishes the need for memorization. So, the first example is counting rectangles. The problem is this. How many rectangles are in the grid in figure 1? The columns of the grid are indexed by letters, so there is column A, which is the further to the left, B, and so on. The rows are indexed by numbers, so there is row 1, which is the lowest one, and so on. In the figure, 3 examples of rectangles are drawn, the red one, green one, and blue one. So I ask you to try and count the rectangles, try and follow the more algorithmic approach, which is just try and count them each one by one, and you will quickly realize that this method is quite tedious. So let's find a better one. So let's follow our proposed approach and start by observing the most basic elements of the problem. We can notice that the red rectangle in figure 1 is composed of the columns A and B and of the rows 4 and 5. Similarly, the green rectangle is composed of the columns B and D and of the rows 2 and 4. So each rectangle is identified by a pair of columns and a pair of rows. Furthermore, for each pair of columns and pair of rows, there is one and only one rectangle. For examples, the columns C and D and the rows 3 and 5 identify the blue rectangle. So, through observation of basic examples, we built a heuristic, which is each rectangle is a pair of columns and a pair of rows. So, now, through the heuristic, we want to build a better algorithm than just counting. Since each rectangle is a pair of columns and a pair of rows, the number of rectangles, which we will call n from now on, is the number of choices of a pair of rows and of a pair of columns. One choice, for example, would be columns AC, rows 1, 5. Now, to calculate n, we first need to compute the number of choices of a pair of columns, which we call NC, and the number of choices of a pair of rows, which we call an R. So let's start from NC. Let's fix column A and count the number of pairs of columns containing A. There are clearly 4 pairs, which are AB, AC, AD, and AE. Now let's fix column B and count the number of pairs containing B. Still, there are 4 pairs which are BA, BC, BD, and BE. Similarly, there are 4 pairs containing C, 4 containing D, and 4 containing E. So we counted 4 times 5 pairs, 4 pairs for each of the 5 columns. Let's notice that with this method, each pair has been counted exactly twice. For example, the pair AB was counted when we first fixed A and then chose B, but also when we first fixed B and then chose A. The pair CD has been counted twice when we first fixed C and then chose D, and then when we first fixed D and then chose C. Therefore, NC is 4 times 5 divided by 2. Since we counted each pair of columns exactly twice, and we counted 20 of them, 4 times 5, 20 divided by 2, 10. Okay. Now, an R can be calculated exactly in the same way. We fix row 1 and count 4 pairs containing it. We do the same for each of the 5 rows and count 20 pairs. Each pair is counted twice, so still 10. Let's notice that we can apply this reasoning to grids with any number of rows and columns. Given 7 columns, NC, number of columns, is 7 times 6 divided by 2. In fact, we fix each of the 7 columns, find for each of them 6 pairs containing it, so 6 times 7, and then since we counted each pair twice, we divide by 2. 6 times 7 divided by 2. Similarly, with 10 rows, we would have an R equal 10 times 9 divided by 2. Let's go back to the original problem. We know that NR and NC are both equal to 10. For a fixed choice of a pair of columns, we have 10 different rectangles, one for each choice of a pair of rows. Since we have 10 choices of a pair of columns, n equals 10 times 10, 100. Okay, we solved our initial problem. But more generally, for any number of rows and columns, n equals nc times nr. In fact, for each fixed pair of columns, we have nr possible rectangles, one for each choice of a pair of rows. Having nc pair of columns, n equal nc times nr. So, what did we do? We started looking at basic examples, built a heuristic with which we derived an algorithm. Through the algorithm, we have been able to better our understanding and solve more problems. For example, we know that with 7 columns and 8 rows, n equals what is shown in the slide. I'm sorry, that 7 times 6 divided by 2 times 8 times 7 divided by 2. So we started with the basic examples. Build a heuristic, derived an algorithm that solves the problem, and understanding the heuristic, we have been able to solve many more similar problems. And through the knowledge of all of these similar problems, we can build a better heuristic and a more general algorithm. In fact, in general, if you have n columns and m rows, n, which is always equal to nc times nr, is equal to n times n minus 1 divided by 2 times m minus 1 divided by 2. And so we solved the problem for every possible grid with how many rows and columns one wants. So look at the basic examples. Build a heuristic, solve the initial problem through an algorithm. Through this algorithm, you can understand more similar problem, and with a vaster data set, we have a more general heuristic because we can solve the grid for how many rows and how many columns, and a more general algorithm because now this formula solves the problem for any grid. Now, I will leave the floor to Simone that will show an analogous example in his field.
Thank you very much, Marco. Yeah, to me, we're not usually taught to deal with algorithms and heuristics in the classics, but actually when we discussed with Marco this example of the various rectangles, we also brought it in a real school, and it was a success. So all of our students understood like our point, not just the formula in that particular problem. So what I like best of this approach is that students learn how to learn, which is a great thing. And by adopting this framework, I managed to identify what students actually do instead of doing what they are supposed to do in their 5 years of high school in Italy when they learn Latin. So in the handout, you can see that there's some context. I'm representing in a schematic fashion the structure of a liceo, a type of various types of Italian high schools where Latin is studied. And since I happen to teach Latin in both a liceo classico, the classical one par excellence, but also in a scientific one, I have quite experience, and there are like hundreds of students of mine who were the basis for this reflection. So if we were all students in our first year of Liceo Scientifico, say at Plinio, where I taught and Marco studied, we would start studying morphology, so memorizing the declensions, which is generally, considered like an old-fashioned thing, a boring one for students, something that doesn't really stimulate them. I cannot say, of course, that studying Latin grammar as mathematics is just a cakewalk or a nice evening at Disneyland, because I would be lying to you all. But at the same time, even though I do not think that the structure of Italian school is perfect, yet I think that there is a reasonable idea behind it. Let's get started in the first year with morphology. Let's study more in-depth syntax in the second year, and in these first 2 years of school, we are supposed to mostly translate and learn grammar. This corresponds, in my opinion, to the first algorithmic stage identified by Marco. So grammar is basically a collection of algorithms and of rules, and I like making an example, the one of ablative, which is usually a tricky case to learn for students because so many complements are expressed via an ablative. And as our first step, we are all students at Liceo Classico or at Scientifico. Let's keep that in mind. We have to learn that there's an expression of place from which, but then also expression of place in which, and an instrumental value or associative value, and so on and so on. You have to memorize a lot of stuff, and that can be tricky. But what's the point of focusing on this? If you are given many unseen passages and you have to translate them. Of course, you have to rely on your memory or on your printed grammar in order to do the basic grammatical analysis of your passage. My student, and not only my students, I think like many students in general, what do they do instead? Well, they ask some internet softwares to perform this analysis in their stead. And of course, they do care about the result. So that's very algorithmic too. But my point is, usually I criticize my students by saying them that, I don't know, they conceive school as something on demand. So they just care about the immediate result. That's how I think society teaches them to see the world. Just you have a remote control, or you can skip stuff you don't like. Well, my impression is that when they skip this part, so when they do not struggle with grammar, when they do not waste their time by analyzing the forms, let's pretend they encounter a genitive rosae. The rosae can also be a dative, singular, a nominative, or vocal in the plural. So of course you have to make hypotheses and then verify them. Well, if one adopts this approach, at some point, one will be able to construct their own heuristics. What's the heuristics of ablative? Well, if we adopt a historical approach, that can be, for instance, true for the years 3 to 5 in Liceo Scientifico, at some point you learn that Latin had originally as many as 8 cases. So there was locative ones, and it's not hard to associate locative with an expression of place in which. And also there was the instrumental. Both of them were absorbed by ablative. If one adopts a comparative approach, maybe this is at university level, but still that's how it works. Well, it's even easier to compare like the Greek genitive or dative with Latin ablative and so on. So of course, once you have this kind of approach to, let's stick to the ablative, well, at some point you don't have to just memorize a long list of complements, because thanks to a long exercise, now you are able to like almost immediately identify the various possibilities. Like, there's something else very important. So a dictionary, a Latin dictionary, is another collection of algorithms. I think that both grammars and dictionaries should be taken by students as suggestions. But instead, with their spontaneous, desperate algorithmic approach, many students see it as like the last resort, just something that can save you, that can give you the mark that allows you to survive to the school year. So what do they do? And not only do they use softwares to analyze the grammar of their passages, and in this way they cannot pass to the next step, but also they look, I would say, in an haphazard fashion for their favorite meaning in the dictionary. And again, nobody teaches them that many dictionaries are arranged their meanings like according to like a chronological order. So whenever after the first 2 years of school we reach the triennio, so the years 3 to 5, we are expected to not only translate unseen passages and to learn grammar and blah, 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 but also to study some anthological passages. So, we study ancient authors from a literary point of view. And in this case, like historical considerations or other types of observations can even further improve our understanding of a given word. A classic example is, many students translate imperator in a bad fashion. And of course, you need to combine a piece of historical information, like before Augustus, we are not authorized to talk about an emperor in Rome, with something grammatical or something that is in the dictionary, which is the meaning of imperator. So of course, when ideally a student reaches year 3 of school, they should be able to remember even quite well the various complements of the ablative, even to shortly illustrate the history of this Latin case, of course, to analyze a passage from a grammatical point of view and to enrich their analysis, with historical considerations. And once you reach this kind of level of knowledge, I think that you have also a heuristic approach to translation. Quite unfortunately, I realized that all of this, let's call them superior, but just quantitatively, forgive me, this superior approach, not from a quality point of view. I'm not a quality type of person. They remain where they are, and to them, Latin grammar remains just, as in some cases, mathematics or physics, something obscure, something not really understandable, something not useful. Finally, a remark which is not really about Latin, but it does influence the way students study Latin. They adopt a different type of algorithm, and teachers try to counter this approach just with a moral argument, and well, it's not a success. So I said that in Italy, there are school reports in January, so the first half of the year is completed, and then you have another school report, the final one, at the end of the year. So students use an algorithmic approach to calculate how bad they can translate something. You pass a Latin test with 6 out of 10. That's the Italian standard. So they're like, well, in the first half, I can get a 4.8 that becomes 5, so that in the second part, I can get a 6. And they're not taking into consideration the fact that if you do not learn the declensions, let's say the first 3 declensions in Latin in the first part, you can never hope to understand anything about Latin in the next years. But yet, this is how things work. So to wrap up everything and to leave the floor again to Marco, I think that the analogy holds that ideally an algorithmic approach can be used as a starting point. Let's say, let's memorize the declension of a noun. Let's memorize the various complements that are translated that are expressed, by an ablative. And then there are superior, improved levels of knowledge that can be reached. How can school encourage students to, not to use an algorithmic approach to their marks? Well, that's an excellent question, and I don't have a plan to reform Italian and European schools at hand yet. Hopefully in the future we will, but still, I think that this kind of analysis really helps understand what students actually do and how they somehow fail, and also how they can be motivated to improve their knowledge, because I'll say this when Marco leaves the floor to me again, but even with apparently boring stuff, just apparently, and I don't agree, of course, like meter, for instance. I mean, I did see many students, even with low grades, I'm saying this plainly, just, calculating long and short syllables by hand. And, they were excited. They were like, oh, teachers, I'm getting it. And so how is it possible? Well, it is possible, and people can get satisfaction from analyzing correctly a text from a grammatical point of view. So heuristics is good also for the morale, not only for for the rational part of this. Now, Marco, I'm leaving the floor to you again. Please go on with the rest of the conversation, not the conversation, of the presentation, whenever you're ready.
Thank you. Do you see the slides?
Yes.
Okay, so we can go on. In the next example, and in all of the successive examples we will bring, we are going to show you how the use of heuristic reasonings, which is often underutilized in our educational system, diminishes the need for memorization of formula, can make mathematics from something that is just boring and formula and monolithic, like they were Tommaso and Leonardo were saying in their paper before. They can make it into something interesting and alive, and in which you have a creative part of reasoning. So the second example are the geometric figures, various geometric figures. The heuristic of this example is that complex geometric figures can be broken down in simpler geometric figures. And knowing the area of the simpler geometric figure, you can calculate, derivate the area of the more complex ones. The complex parts of the heuristic are the geometric figures and their area. The connection between the parts are how one figure can be decomposed in terms of the other. So, as it is well known, the area of the rectangle is b times h, base times height. Let's now look at figure 3. This is a parallelogram, and if you cut the triangle marked with a green dot and paste it on the triangle marked with a yellow dot, you will see that the area of the parallelogram is equal to the area of a rectangle with base b and height h. Therefore, a equal b times h still. Okay. As shown now in figure 4, the union of two identical triangles makes a parallelogram of side B and height h. Therefore, the area of the triangle is half the area of the parallelogram. Therefore, the area is B times h divided by 2. Now, let's go to the next figure, figure 5, and observe that two identical trapezies make a parallelogram with a base, long, major base plus minor base, and height h. So the area of the trapeze is half the area of the parallelogram. Therefore, area equals b, major base plus minor base times h divided by 2. So let's now go and calculate the area of a circle of radius r. To do that, we need to remember that the circumference, its length, it's equal to 2 pi r. Okay. Let's divide the circle in 4 equal parts, as shown in figure 6a, and rearrange them as shown in figure 6b. The superior part has length c over 2, since it contains 2 of the 4 equal arcs that make the circumference. The same goes for the inferior part, and the side's length is r, since they are the radius. Let's now go to figure 7b. In figure 7b, we divide the circle in 8 equal parts, and then we rearrange them as shown in figure 7b. In 7b, the superior part has still length c over 2, since it's composed of 4 of the h equal arcs, and the sides are still long r, since they are the radius. Okay. If we keep doing this, dividing the circle in 16, 32, 64, and so on parts, the rearranged figure will converge to a rectangle with height r and length and base c over 2, as shown in figure 8. Therefore, the area of the circle is c over 2 times r, and remembering c equals 2 pi r, we have area equals pi r squared. So, in all of this form, you don't need to learn basically any of the geometric formula. You are usually just taught as an algorithm. You have to learn them all by memory, but most, if not all, of the formula can be derived by just knowing the area of the rectangle. And this kind of reasoning lets you not only know more stuff, remembering less, but makes you able to derive more stuff and understand more stuff on your own, to be intellectually independent, because you can think and understand and derive on your own instead of just remembering a list of stuff. Now, for the next next example, it has been cited today. It's Pythagoras' theorem, and it's often given just as a pure algorithm, just a formula. As it was said before, there are over 100 proofs, and usually the student sees none of them. So, what does the Pythagoras theorem state? It states for any given right triangle, which we will call T, which has catetes A and B, and hypotenuse I, it holds I squared equals A squared plus B squared, as you can see, exemplified in figure 9. Now, this as a heuristic. The heuristic is that there is a certain geometric connection shown in figure 10 between right triangles and squares, and through that we will derive the formula. What is the geometric connection? There is a big square shown in figure 10, which we call uppercase Q. Each of its sides has length A plus B, being composed of a side of length A and of a side of length B of the triangle T. Uppercase Q is composed of 4 copies of the triangle T and of a square of side I. Therefore, the area of uppercase Q can be calculated in 2 different ways. In one way, as you can calculate, since it is side squared, its side is A plus B, its side squared equals, as you can see in the calculation on the slide, A plus B squared equals A squared plus B squared plus 2AB, and this equals the area of the big square uppercase Q. But on the other hand, the area of the big square AQ can be calculated as the area of the smaller square plus 4 times the area of T. The area of the smaller square having its side I, it's I squared. The area of T being it a right triangle, and so being A, its height, it's B times A divided by 2. So we have that the area of big square is also equal to I squared plus 4 times A times B divided by 2, which equals I squared plus 2AB. So we have these 2 equalities. A square equals something. The area of uppercase Q equals something, and the area of uppercase Q equals something else. You can say that these two things are equal. So we have A squared plus B squared plus 2AB equals E squared plus 2AB, which is just the right hand of these 2 equations that are equal. So we put them one equal to the other, as you can see. And so we have this equation. And then since we have plus 2AB from on both sides, we can take it away. And what remains is A squared plus B squared equals I squared, which is the famous Pythagoras theorem. And again, more formulas can be derived without need of memorization, but with true understanding of the problem. Now I will leave the floor again to Simone, which will talk about an analogous example in his field.
Yeah, thanks again, Marco. To be fair, with this second set of examples, I was originally struggling a little bit because, in the first case, it was, to me, relatively straightforward to identify, the various steps identified by Marco too. So you start from algorithms, then you adopt a heuristic approach, which in turn helps you to improve your algorithm. So I decided to pick meter, Greek and Latin meter, and I think that the teaching and learning of Greek meter partly works in the way already described for the ablative. So of course, you start by dividing into syllables. And again, if you have already acquired the grammatical knowledge that teaches you like the length of certain syllables, of certain vowels and so on, it's much easier to deal with meter. Otherwise, students, usually they start studying meter in the third year, and without the necessary knowledge of the first 2 years, I don't want to say it's impossible, it's a real struggle. And so if one adopts this original algorithmic approach by dividing into syllables, calculating the length and so on, and resulting to like handbooks of meter and whatever, at some point you can reach the level when you can simply read at impromptu any hexameter, for instance, or a ledger pentameter, except those presented by our colleague Tom. In that case, my brain stops working and I cannot identify an elegiac meter anymore. But except those, all the other ones are perfectly easy to be identified. But now we want to demonstrate something else, that like if we do not just adopt an algorithmic approach, but you also combine it with a heuristic one, your life is simpler. And so we had this conversation a few days ago, and the example of dactyloepitritis helped me with the pronunciation, by the way, or catenoplean epitritis came to my mind. Now, we have a marvelous library containing the translation of this beautiful handbook of metrics and rhythmics, so I resorted to it. Unfortunately, I have some, handwritten notes, because I followed a course held by Liana Lomiento in 2013. They are in Rome, stuck somewhere, buried under tons of paper. So I'm really sorry that, I'm not delving more into detail. So I'm not dealing, more in detail with this issue. When in Rome, I look again at the notes containing several examples supporting my point. So I will just show you the idea, dactyloepitritis are this, relatively rare. This is relatively rare meter, and it is employed by certain poets. I'm taking Bakilides here as just an example. And when I was a master's student, at some point, my professors were like, "Oh well, this is the meter. We adopt a descriptive approach," which seems like a nice term to designate something. And I was like, yeah, but how is it describing the meter, and what is it actually describing? So if you look at page 2 of the handout, there are 2 pictures. The first one just reads a dactyloepitriti, and so on. Well, this really seems like a relatively easy thing, because there are a few sequences of long and short syllables. There is also something quite evilish called anceps interpositum. What is that? Is something never identified as such by ancient commentators, but still it was devised by Paul Mas. My greatest respects to the genius of classical philology, and still this approach has problems. So although you have like a lowercase e, uppercase D, and D1, D2, so just 5 basic elements plus an anceps interpositum, represented by an X, so it can be 1 or 2 syllables, where, well, when you have a look at the actual scheme, this doesn't really look simple. It's quite messy, and I was a student. I look at this very edition by Mela, and I was like, I don't understand this. Then I had the pleasure to discover an alternative interpretation, and it's the one provided by Bruno Gentili and Liana Lomiento. And as in the case of the ablative, where at some point the historical approach to grammar helped you construct a heuristic, well, here the case is the same. So Schnell, Mellers, and Mas approach is based just on their own personal impression. Like, I look at the text, I personally identify my favorite sequences of long and short syllables, and that's the descriptive approach. On the other hand, Bruno Gentili and Liana Lomiento read the ancient sources on Greek meter. Nowadays, they are usually treated like, well, they didn't really know, they're late antique sources or imperial sources. They weren't fully aware of quantities. So it's relatively easy to simply overlook them. but the ancient sources, are actually works written by people who were native speakers of the language, even though they might have already lost the sense of quantity. Still, they did know their literature, and they understood the language and society possibly even better than us. Their theory provides us not with lowercase e and so on, but with 9 metra prototypa. So, dactyl, spondy, all the basic sequences of Greek meter that we know. And by combining this metra prototypa, you can form many lyric and non-lyric verses in Greek and Latin. In particular, when it comes to the so-called dactyloepitritis, the analysis provided by Bruno Gentili and Liana Lomiento, persuasively argues that there are no dactyls conceived as such, and there is no such a thing as an anceps interpositum or whatever. They analyze the corpus of poetical works written with this meter, and with their analysis, there are many less exceptional cases. So their historical approach explains almost all the problematic lines that, according to dactyloepitritis, were sort of exceptions. Again, I know I should bring examples. I hope you will forgive me, because if I'm presenting on something, I should be ready to, fight to death in favor of my argument. I will, but my notes are in Rome. And again, I suppose that my poor mother, was really in troubles when she was looking for these notes. But the handbook by Gentili and Lomiento provides you with all necessary criticism, a well-informed piece of scholarship about dactyloepitritis. And again, there are cases, for instance, a small poetical composition by Aristotle, who he wrote for a friend of his, Hermias, a tyrant who had died. Well, it's written in Catenopion Epitritis, and as a bachelor student, I tried to read that piece of poetry by adopting the dactyloepitritis approach. It was a mess. Honestly, I was like, I need to quit with the classics. Not the first time that meter had this effect on me, but so hopefully a revised theory, a more sound one, more effective one, can help students, even well-motivated one, as I used to be, to understand complicated things. And so I'm concluding this part. Just I'm observing that, of course, being Latin or Greek a different thing, if you compare that to mathematics. When we talk about heuristics in the like Latin or Greek teaching and learning, usually a historical approach is entailed. So, for instance, in the preface to the English translation of this handbook, the translator of Metrics and Rhythmics said that basically, in this book, Gentili and Lomiento created a new historical theory of Greek meter that was superseding the previous one that was abstract. And I think that this kind of distinction can be at least partly, overlapped with our own distinction between an algorithmic, a purely algorithmic approach and a heuristic one. Provided that, of course, there is a continuum between what we call algorithm and what we call heuristics, and that the differences are mostly quantitative. Anyway, in this case, heuristic approach, what we today define as heuristic approach, really helps you with the meter, whereas the so-called descriptive approach, an impressionistic one, to me, doesn't really help you. It makes things more complicated. So even in this respect, the analogy holds. Now, Marco, if you have any conclusions, I'm leaving for the last time the floor to you, and then, well, we can move to the question and answer sections also, because, well, yeah, it's definitely the right time to do so.
I'll be very quick. I'd just like to say that I think that what we say can be applied analogously to most, if not all, fields of knowledge, research, and especially teaching, not only Greek, Latin, and math. Furthermore, I'd like to say that I personally think we are looking at an incredible waste of time, energy, potential, since we are taking millions of students, putting them for 10 years or more in class for most of their weeks. And instead of making them think, teaching them how to think, how to be truly human, to have a curiosity, to searching to your own, use your critical thinking skills, and be able to reason. We are making them just someone who can execute algorithms and instruction without batting an eye, killing the curiosity and turning potentially brilliant researcher or however people with intelligence and capacity to reason into someone who doesn't think themselves able to understand, and so they don't even need to try and understand, they just follow instructions. And I think this is a big problem. So I will end with this. Thank you for your attention. Thank you for having me. Thank you, Simone, for organizing all of this.
Well, thanks, Marco. And well, I would like to add nothing because I do, of course, agree with you. In our conversations, we always talk about this. Like if you give students a merely algorithmic approach, you are producing good instruments, good tools that can be used, that can be receive orders, which is helpful. Like society also requires that, but not only. And since we are all scientists and more generally curious people, sometimes even nerds, it's late so I can start saying things at random. Well, so there is something more. And I hope that this beautiful conversation can be, just another step towards a more global and again, unifying approach to our own disciplines. Anyway, thanks everybody for the attention. I think that now there can be room for a question and answers section concerning this paper, but more generally about all the presentations of today's event. So we have time, and well, thanks everybody.